Welcome to online lecture series in organic chemistry. In earlier video, we discussed about the basic steps involved in homogeneous catalysis. In this video, I am going to discuss the example of homogeneous catalysis, that is hydrogenation of alkene to alkane by using Wilkinson catalyst. The composition of Wilkinson catalyst is chlorotris triphenyl phosphine rhodium first. This is the name of the Wilkinson catalyst. Actually, Wilkinson catalyst, it is 4 coordinate square planar 16 electron coordinately unsaturated transition metal complex. As such, this is not organometallic compound because there is no any metal carbon bond, but this is transition metal complex. It is the first homogeneous catalyst that is used for the hydrogenation of alkene. Now, during hydrogenation of alkene to alkane, it is treated with hydrogen in presence of Wilkinson catalyst, that is chlorotris triphenyl phosphine rhodium 1. Then we get an alkane. There is a formation of alkane. Now, what is the mechanism of this reaction? This reaction actually follows 5 steps. Now, step 1. In step 1, or first step, in aqueous solution, the 4 coordinate Wilkinson catalyst undergoes dissociation and there is a formation of 3 coordinate 14 electron species, and there is a loss of 1 triphenyl phosphine group, and we get a tri-coordinate compound. This is the tri-coordinate. This is the tetracoordinate. Coordination number is 4, and for this actually 1 triphenyl phosphine is lost and we get tri-coordinate complex. So this is 16 electron because rhodium 9, then this chloro 1. There are 3 triphenyl phosphine group. Each triphenyl phosphine donates 2 electrons, so 2 into 3, that is 6. 6 plus 1, 7 plus 9, that is 16 electron. So 16 electron complex gets converted into 14 electron tri-coordinate complex. Again rhodium 9, this chloride 1 triphenyl phosphine. Each triphenyl phosphine contributes 2 electrons, so 2 to the 4. 4 plus 1, 5. 5 plus 9, that is 14. So this is the step 1. This step can be, in short, actually this triphenyl phosphine group, it is denoted by only P. For simplicity, we are denoting this PPH3 as a P. In that case, we can write RHClP3. This P stands for triphenyl phosphine group. This is the tetracoordinate complex, 16 electron tetracoordinate complex gets converted into tri-coordinate 14 electron complex with the loss of 1 phosphine group. This is the step 1. Now second step. In second step, the tri-coordinate 14 electron species undergoes oxidative addition of 1 molecule of hydrogen, and there is a formation of 5 coordinate 16 electron dihydrido complex. This is the dihydrido complex. There is a addition of 2 hydrogen atoms, or 2 hydrides I will say, to the rhodium, and tri-coordinate complex directly converted into 5 coordinate complex, and this is reversible. When these 2 hydrogens are lost, again we get tri-coordinate complex. So tri-coordinate, it is converted into pentacoordinate. So coordination number increases by 2. Even oxidation state of rhodium also increases by 2. Here oxidation state of rhodium is +1, and in this 5 coordinate complex, its oxidation state is +3. Coordination number here 3 because 3 ligands are attached, monodentate ligands, and in product side there are 5 ligands, so coordination number is 5. So this is the step second. Now the step 3. The 5 coordinate complex now has a vacant coordination site, and carbon-carbon double bond can coordinate at this site. Actually, the coordination number of rhodium is it can be expanded up to 6. So there is a one vacant site available at rhodium, and therefore the dihaptic alkene ligand, it can be coordinated with this rhodium to get 6 coordinated complex. So this is the 5 coordinate complex with 16 electron. When it comes in contact with alkene, coordination number of rhodium increase to 6, and we get 6 coordinated complex, and there is a coordination of this alkene with this rhodium. So here one molecule of alkene gets coordinated, and this alkene coordination results in the formation of 6 coordinate 18 electron, I will say here, activated intermediate of alkene complex. This is the intermediate, and coordination number of rhodium here it is 6. So coordination number increases from 5 to 6. This is the step number 3. Now step number 4. Now here in step number 4, alkene coordination actually results in the weakening and breaking of double bond between 2 carbon atoms. There is a breaking of double bond between these 2 carbon atoms, and the alkene intermediate complex follows 1,2 insertion, and there is a formation of 16 electron 5 coordinate complex. So this double bond breaks, and there is a formation of, actually this bond now it is formed with one of the carbon, and we get 1,2 insertion like this. So this is the pi coordinated, or this rhodium forms bond with both the carbon atoms because it is dihaptic ligand. After 1,2 insertion, now rhodium forms the bond with one carbon, and this is 1,2 insertion, rhodium attached to carbon number 1, hydrogen attached to carbon number 2. So this is 1,2 insertion. One of the hydrogen, it is migrated to second carbon, so, and rhodium attached to first. So it is 1,2 insertion step, and here one hydride actually, or hydrogen atom, migrates from rhodium ion, rhodium +1 ion, and gets bonded to the carbon atom of alkene molecule, and this is the rate determining step. This is slow step. Now step number 5. Now here there is a migration of hydrogen linked to rhodium beta, actually rhodium to beta carbon atom of coordinated alkene like this. So here there is a migration of this hydrogen attached to rhodium to the carbon atom, and there is a formation of product, that is alkane, and there is a again regeneration of 3 coordinate complex, and this is the reductive elimination step. This 3 coordinated complex, or this regenerated 3 coordinated complex, again reacts with hydrogen as per step number 1 explained earlier, and the cycle is repeated again. So continuously there is a conversion of alkene to alkane. So all the 5 steps, these are summarized like this. So here, as explained in step 1, there is an equilibrium between tetracoordinate complex of rhodium and tricoordinate complex of rhodium. This tricoordinate complex of rhodium, by oxidative addition of hydrogen, gets converted into this species where there is a addition of 2 hydrides to the rhodium, and we get a 5 coordinate complex, which on coordination with alkene there is a formation of 6 coordinated complex where rhodium, it is attached to both the carbon atoms because it is bidentate ligand. Alkene is a bidentate ligand. This is the 6 coordinate complex. This step is also very important because actually in this step there is a formation of activated intermediate of alkene complex. This is activated intermediate. After 1,2 insertion, we get this complex, which is a 5 coordinated complex again, and after hydrogen migration or 1,2 migration and reductive elimination, there is a formation of tricoordinated rhodium complex. At the same time, there is a formation of alkane. Again, this tricoordinated rhodium complex, after oxidative addition, forms the 5 coordinated complex, and the cycle is repeated. So continuously the alkene, it is converted into alkane. Okay, so this is the 5-step hydrogenation process using Wilkinson catalyst. Here Wilkinson catalyst act as a homogeneous catalyst. Actually, there are some disadvantages of this Wilkinson catalysis. The first disadvantage is, so it is very difficult to separate Wilkinson catalyst from the products or reactants or reaction mixture, and it is very difficult to reuse Wilkinson catalyst, and therefore the process is very expensive. Basically, rhodium complex, it is expensive, and at the same time it cannot be separated and reused. This is the main drawback of this Wilkinson catalyst. And here there is an end of organometallic compounds.